So, well, today I would like just to tell you about our work of nanophotonic, how we develop nanophotonic biosensor for this ultrasensitive diagnostic at the point of need. And of course, I'm going to focus mainly in the diagnostics of bacteria, of infections, and also about all our work that we have been doing in the COVID-19 detection. So I think it's very clear for all of you what happened in this pandemic. Still, we are in the pandemic. But if you remember at the beginning of the pandemic, we saw a very long lines to get a PCR analysis, even if we have so many PCR machines and so many laboratories. But the main problem with the diagnostic is that this is a centralized diagnostic, so the PCR has to be done in a centralized facility. So this is what we are just focusing as a main problem in the clinical diagnostic, is that in any case, we always need to see our medical doctor, our family doctor, and then depending on your disease or your conditions, you need to go for sophisticated techniques or for sophisticated analysis. Even if we have very, very good and excellent techniques, like for example, if you need a colonoscopy or you need to just resonant imaging and whatever, all these laboratory techniques, the main problem is they are time consuming, they need a high sample volume from the patient, they need trained personnel, they need laboratory installation, and sometimes even this instrumentation is really expensive. So this is what we have been also looking during the pandemic, that sometimes we need to be waiting for the diagnostic from hours to days. So means that for many diseases, for example, for infections, there is a late drug administration, and especially when you have a big problem, like in the case of the pandemic, is all these centralized laboratories are completely inefficient for population screening, for a large population screening. So what we see as a solution for the future, especially after the pandemic, or what we call the post-pandemic times, is that we need point-of-care biosensor technology able to replace and to provide this decentralized diagnosis. So the idea is that we can make this analysis just using a simple, just a drop of our blood, of our urine, of our tears, and then that we can deploy in these very small point-of-care devices, and then we can get just an instant diagnostic with this technology. But of course, I mean, we need that these point-of-care devices are enough reliable, and also that they have a very high sensitivity, even if they have a very fast time to result. And also they are able to provide a quantitative result, not only a yes or no result. So biosensors are the technology that they're able to provide these point-of-care technologies. And we know that the point-of-care diagnostic will improve, simplify, and accelerate the healthcare flow and clinical management. So I don't need to explain what is a biosensor, just to remember that in a biosensor, we have a physical transducer in contact with a selective biological receptor layer that gives you the selectivity in the analysis in a complex sample. And there are many different kinds of biosensors that are commercialized. Probably the most famous one is the glucose biosensor. And even now we are using, widely used this rapid test for the COVID-19. But of course, in our case, we see that the photonic biosensor using light, using photonics is probably one of the most powerful technologies in order to supply this, to fabricate this optical biosensor and to fabricate this point-of-care testing device. And why I'm saying that is mainly because using optics, you can get a ultra sensitivity, and this is very important in the case of the point-of-care diagnostic. Of course, we can go for miniaturization, for integration in latency, for multiplexing capabilities. But more importantly, we can provide a label-free analysis, no labeling, no fluorescent labels, no amplification. So that the idea using this powerful photonics technology, and then providing also a real-time analysis. Probably in the optical biosensor field, what we're using mainly is the magnetic wave principle, where we're using just the part of the electromagnetic field that is going out from an optical waveguide. Normally, this magnetic probe has like a penetration between 100 to 900 nanometers. So we are able to sense any refractive index change that's taking place during a biomolecular interaction. So any binding event is going to be translated in a change in the refractive index taking place in this area of the evanescent wave. And then means that then this chain of the refractive index is going to induce any chain of optical parameters. So we can see at the end just a change in the intensity, the polarization, in the phase, in the resonant momentum, whatever. But then we can have this label-free and real-time analysis. So in my group, we are working in making these photonics evanescent wave chips. But of course, we have to figure out that it's not only to make the biosensor, to make the sensor, and then to allocate also the biological receptor. We have to do a complete engineering development because it's the main point in a point of care. We need to introduce the microfluidic cartridge. We need to introduce also some lasers, so photodetectors, electronics, battery, and so on. So means that this is a complete engineering development, not only to make a device. And in our case, of course, we are introducing here this nanophotonic sensor chip, and we're using, in my group, we're focusing in two main technologies. So we're working plasmonic, and we're using also silicon photonics chip in order to make this powerful technology. So in the case of the plasmonic technology, we developed just a standard SPR biosensor, where we just use this standard SPR sensor with this gold layer of only 45 nanometer. But in my group, we just fabricate the complete instrument. At this moment, this is our last model where we have 2 channels SPR. So we fabricate all the gold sensor chip, we provide the electronics. We're expert in all the biofunctionalization protocol in order to be able to operate in real sample, and then we provide also the readout with a tablet or just a mobile phone. We develop also strong localized SPR technology. We are not using nanoparticle, we are using nanostructuring of gold, and we are expert in fabricating gold nanodiscs and also providing using nanograting fabricated over a Blu-ray disc. And with this technology, we are able to provide 1 channel, multiplex channels. So this is just one of the instruments that we developed with this plasmonic technology. Just to summarize, we're making the fabrication with a metallic section. See the complete in-house design and assembly, and then we make this compact and portable platform and user-friendly. So you can see all our development also in our publication. The second technology that we are using, a technology that was invented in my lab using silicon photonics technology, is what we call a bimodal waveguide interferometer. And in that case, we are using a silicon nitride waveguide. And in this way, waveguide, what we're doing is the following: we are launching just a single mode of the light. We create a step junction in the waveguide, and then we excitate the first mode of the light. So from here, we have 2 modes of the light. Fundamental mode, first mode, and they are traveling in the sensing area of the interferometer, and at the end they produce an interference pattern. So this is just a single channel waveguide, but we are able to make an interferometric detection just by repeating between the 2 modes, the fundamental modes and the first mode of the light. We're fabricating this waveguide in order to control these 2 modes of the light and the polarization using silicon nitride technology, starting with a silicon nitride waveguide of only 150 nanometer in the single mode part, and then we grow to 340 nanometer in the bimodal part. Our waveguide has a width of only 3 microns, but we have a rip, a height in the waveguide between 1 to 3 nanometers. The only way to be sure that we have only these 2 modes propagating, and we can control the propagation. We have now a very robust and reproducible silicon nitride technology that is fabricating in our clean room facilities. So we fabricate this kind of the wafer level, this kind of chip, where we have 20 biosensors in parallel. We have demonstrated already that we can achieve in a labor-free, so remember, no amplification, real time. We can going down to a limit of detection to 10⁻⁸ refractive index units. So means that our technology is suitable for the detection in the very low picogram per milliliter range. And this one probably is one of the most sensitive evanescent wave sensor that has been presented. It's a very simple photonic interferometric sensor that has a high level of multiplexing operating in the visible range, and we can produce in our clean room facility at a mass level. So with these 2 technologies, and we're of course, we have also tackled the problem of engineering and to have time to explain in detail, but of course, we are not only producing the sensor, working also in the polymer microfluidics. As I said before, we have a very strong expertise in the surface bioanalyzation to be able to operate our cartridge directly with real samples from the patients. We developed the cartridge, we developed also some techniques for the packaging and storage of the biosensor chip. We work on the light coupling, modulation of the light, because it's an interferometric readout, and we make a linear signal, and of course, on the processing of the signal and on the electronic software and so on. Okay, so what we're doing with our technologies is mainly working now in the diagnosis of infection diseases. Well, I think I have to explain here in this forum, but as you know, we have one of the main problems that we are having is the increase of the number of infections, mainly of the nosocomial infection, the hospital-acquired infections. Between at least here in Europe, the 7 to 10% of the hospitalized patients will acquire one of these infections, and then and also there is a probability that most of these patients, if they have a larger stay in the hospital, or for example in the intensive care unit, they will develop also an infection due to resistant bacteria. And as you know, sepsis is one of the main problem, health problem that we're facing now, with more than 11 million of deaths in the year 2017. And there is some projections that probably in the 2050, there are going to be more people dying due to this antimicrobial resistant infection that's from cancer. So we have really a problem in the management of this detection of this infection. Also, as I said at the beginning, main problem with infections is that the current diagnostic technique that we have, they are very good, but the problem is that they are centralized, they are very slow, they are very labor intensive, and then the problem is we have a delayed diagnosis and intervention to these pathogens, and that's the reason why we propose to use this excellent technology for the fast identification and quantification of bacteria, and second, the fast identification of the antibiotic resistant profile. And in my group, we have already demonstrated, for example, how we can use this silicon photonics technology for the fast identification of quantification of bacteria using, for example, monoclonal antibodies. We have been able to detect the E. coli bacteria in acidic fluid from pathogens. Just taking this acidic fluid directly from circulating pathogens. We are collaborating with a major public hospital here in Barcelona, and then we have been able to demonstrate that with one single step assay, we are able to achieve a limit of detection of only 4 CTU of raw bacteria per milliliter, directly in the acidic fluid of the patient. We have also demonstrated also how our technology is suitable to distinguish between, for example, in the case of the Staphylococcus aureus, that is resistant to methicillin. This is the MRSA, which is the most predominant infecting bacteria with this that is resistant to antibiotics. And then with our technology, I'm using just a specific aptamer to the protein in the envelope of the bacteria PDP2A. We have been able to detect until a limit of detection of only 30 CTU per milliliter, but also we can differentiate without any problem between the resistant and the non-resistant strain of this Staphylococcus aureus. So the analysis time is less than 25 minutes. We are taking only between 150 to 150 microliters of the sample pattern. And as I say, this is a direct detection, a specific recognition with no amplification and a label-free format. In a European project that we finished a few years ago, we try to combine plasmonic also with interferometric readout, and we fabricate this point of care optical platform where we were able also to detect the E. coli related to the sepsis infection. And then with this technology, we were able to make even an acute categorization of the sepsis patient, and then we can differentiate with our technologies about the people that are healthy people, having a systematic inflammatory disease, and the people just getting sepsis. So we were using here only 10 microliters of the sample volume. We're using the plasma from the patients, And then we have a very fast and one-step on-site quantification because the point of care was deployed at the hospital. We're working with our colleagues at the hospital, and we were able also to make this rapid quantification and in one step. It was done from bacteria for E. coli, but as well we were also detecting other sepsis protein biomarkers. You can see all the results also in our publication. What we're working just now is trying to offer in a new project funded by the European and by the Spanish government is try to provide this point of care diagnostic where we can detect, making a high sensitivity detection of bacteria. We are going to provide also a rapid antibiotic susceptibility test, but also we are monitoring the antimicrobial therapy of the corresponding antibiotics. So we're going to see how we're monitoring already how is the level of the antibiotic is decreasing or increasing in the patient sample. So just to start finalizing my presentation, I want also to tell you a little bit what we have been doing in the diagnosis of COVID-19 during the pandemic. So well as of course, this is also well known for everybody. We know that the SARS-CoV-2 has been mainly identified by PCR. PCR is an excellent technique, but the problem is time consuming. You need lab installation and then personnel. The situation was alleviated almost 1 year ago because then the many rapid tests were going to the market, mainly for the antigen tests and the antibiotic and the antibody tests, immunoglobulin tests. But then the main problem with these rapid tests, they have a limited sensitivity and they provide only a yes or no, you are infected or not, but no quantification. So we thought that with a point of care for the biosensor will be possible to make this very easy diagnostic at the point of need with a very high sensitivity, selectivity, but it's more important with quantification. We're able to provide what is the viral load that each person infected can have in any moment. And also the diagnostic is going to be very fast. In a minute, we can give the analysis. So we worked on European project, an express European project from the beginning of the pandemic in 2020, and then we have been working in 3 different biosensors in parallel. So we have been developing a one for the direct virus detection. So we just making a capture of the whole SARS-CoV-2 virus in one step and in real time. And then we have been developing also a PCR-free genomic analysis. We're just immobilizing the sequences specific to the SARS-CoV-2. The idea is that we can do a multiplex capability in this biosensor to differentiate from other virus, just in comparison with flu or with influenza. And then we have developed also a serological biosensor where we can detect and quantify the number of immunoglobulins that in blood cells from the patient that have been able to produce as a consequence of the infection. So I just wanted to show our main
minutes, Laura.
Okay, sorry, just finishing. Okay, yeah, this is the detection of the SARS-CoV-2. We're using ultraviolet inactivated SARS-CoV-2 in our installation because we have a biosafety lab in my group, in my laboratory. And then we're using a specific nanobodies as bioreceptor. And with this, we have been able to detect with limited detection, just below 100 virus particles per milliliter. So we have, an excellent dynamic range. So we can go for a limit of detection from 200 in 100 to 10 to 7 virus particle with this biosensor. We have been adapted also to the different variants for the SARS-CoV-2. So our colleagues in Spain adapting all the nanobodies to the different variants until now, so we can differentiate between the original from Wuhan and then the Delta, the Alpha, Gamma, and now we are trying also to do with the Omicron. So we have excellent result, excellent sensitivity. So this is something now we're trying to do. We're doing all the clinical validation with this biosensor, but the biosensor is really working well and should be able to detect even in the first date of the infection the number of viral particles from each pathogen. We are developing this also the genomic virus detection And we are defining 3 different genes. So we have also very good sensitivity. This is under development. And then just to finish, just that we are developers of serological biosensor that have been published recently in analytical chemistry, where we combine different viral antigens, the N protein, RBD peptide, and with this we have been able to achieve a serological biosensor with a sensitivity of 90%, specificity of 100%, and more importantly, we provide a quantification, so we know how the amount of immunoglobulin that each person is able to produce, the immunological system, and we have doing this validation with hundreds of samples from the main public hospital here in Barcelona. Okay, so just to finish, this is just the summary that we have this photonic biosensor for virus detection and also for serological detection. But to finish, I hope that means that I have demonstrated that the point of care biosensor, I think, is going to be required for the fast, direct, level-free, and high sensitivity, low sample volume, and massive diagnostic for the post-pandemic era. And I think that the biosensor is one of the most excellent technology able to provide all this, what we need for the future. And just to finalize, I want to just to thank to all my group that we have been really working during all the pandemic without no confinement. So we have been working since March 2020 in the lab to develop all this technology. And at this stage, we are also doing just a technological transfer for the commercialization of the technology. And just to be proud that more than 85% of my group are women from the different specialties. So thank you for your attention.